Hi, I'm Craig Rowland from Sandfly Security, and today I'm here to give you a talk that I recently gave in Oslo, Norway at the first Cold Incident Response Conference, which happened in October of 2025. Now, this conference didn't have any video recordings of the presentations happening, so this is basically a revamp of the presentation as I gave it at the conference, along with some additional information that I couldn't actually cover at the conference due to time constraints. Now, the thing to understand about what I'm presenting to you today is essentially these are command line forensic tactics that you can use to help decloak stealth rootkits that might be operating on a Linux host. I'm not saying that this is a type of thing you want to do at scale. This presentation is more for the incident responders that are kind of the tip of the spear. You've been called in to investigate a host that's acting a little bit funny. This presentation is going to have a lot of quick techniques you can use very rapidly to determine whether or not that host might have something going on that needs a deeper investigation. So for today's presentation, we're going to be talking about a Chinese stealth rootkit that was used to attack a lot of South Korean infrastructure and perhaps other infrastructure in the Asia-Pac region. This was a Linux stealth rootkit in the strictest sense of the word. It actually hid processes and other activity happening on the box. And this presentation covers that rootkit that was issued in the Phrack magazine. There was a huge data leak that happened in Phrack. They basically cloned about 4 gigabytes of active compromise, attack, credentials, and other tradecraft from a suspected Chinese hacker who might also have been working with the North Koreans. We don't know yet, but they think it was probably China. And as a result of that data leak, they had a lot of information put out there in terms of the infrastructure being targeted in South Korea and other regions. This includes things like certificates, credentials that they were stealing, malware that they were using. And in particular, there was one piece of malware on that system that was targeting Linux. And this was a full-on stealth rootkit, likely based on the Reptile stealth rootkit framework, which you could find on GitHub if you do a search for it. This presentation is going to be covering this rootkit in terms of how it was hiding on the box, but the general techniques work across a wide variety of these styles of stealth rootkit, so they're going to have general application for anyone who wants to watch. Now, what's interesting about rootkits, they have a lot of generic kind of common features among them that kind of intimidate a lot of people, but hopefully by the end of this presentation, you'll find out they're not too intimidating at all once you start peeling back the layers. Now, first of all these rootkits are going to have very common issues. They're going to hide their module that once they load themselves, they're going to hide files and directories, they're going to hide processes. They frequently have something called a magic packet activation, which is basically a specially crafted packet that is sent to the system to allow it to basically activate a backdoor. And that backdoor, once it's activated, is going to have evasive features as well to make sure you don't see it running when it is actually on the box. Now, the problem a lot of these rootkits have is they are what I call juggling hand grenades. Essentially, they can hide from casual detection and even some focus detection efforts, but because they're interacting with the kernel in a way that it doesn't want to be worked like, basically Linux is the premier open source operating system in the world, where open is the operative word. It does not like to hide things. So because these kernel rootkits are coming in and trying to hide, they are breaking a lot of how that kernel wants to work and how the operating system wants to present itself to the user. So this is going to cause system stability impacts. They tend to be fragile and tied to specific kernel versions. So even if you were to update that kernel, it might actually break the entire rootkit. And lastly here, this is the thing I emphasize a lot. Once you find one element that there's a rootkit operating on the box, and it's very obvious that the system's been compromised because Linux does not hide files. So if you find evidence of someone hiding a file, hiding a process, hiding network connection, hiding data, at that point, you know with extremely high certainty that that system is likely compromised. It wouldn't have happened by accident. So the whole point of the presentation today is how do we turn someone hiding in the woods in perfect camouflage into basically a clown? Like, how do we make it like really obvious where we make the hiding a liability? And that's one of the things I work at this, why I look at this as a detection engineer. A lot of people think incorrectly that the purpose of intrusion detection and detection engineering is to find every conceivable thing that someone is going to do to a system. That is actually incorrect. The goal of a good detection engineer is to try to find enough problems on a system that indicate a compromise, that you're making the window of options available to an attacker very, very small they can operate in without being caught. So my goal as a detection engineer is not to catch everything, because you're not going to catch everything, and there's always going to be a new version of the rootkits that are going to do something different, The goal of a good detection engineer is to make it so difficult for someone to come in and pull off an easy compromise that they're going to make a mistake and they're going to get caught, and like I said, turning them into this clown. So we're going to adopt 3 main principles of Linux rootkit hunting, and these are things I've used through my entire career in the network intrusion detection and incident response space. I think changing this way of thinking is really going to help you when you make some of your rules and doing your investigation. First of all, we're going to focus on what I call data leaks. These are things that the hiding activity does not completely hide from observation, and it's leaking out real information about what's actually going on. The second one, and this is a really big deal because this happens a lot, inconsistent answers. What I mean by inconsistent answers is essentially this idea that we're going to ask the same question multiple different ways, and we're going to make sure all the answers are the same. This is identical to how a police interrogation works, meaning that if they pull a suspect in, they don't just say, "Where were you at 10 last night?" They say, "Where were you at 10 last night? And why did someone see your car at 10 last night in this particular location?" Or, "Your neighbor saw you here. What were you doing at that location?" Right? They ask the same question multiple different ways, and they want to make sure all the answers make sense. We do the same thing on the Linux side. We're asked multiple questions to make sure they all make sense. And this is a really important part of finding Linux stealth rootkits that are trying to hide, because they never hide completely. There's always something they miss, has been my experience. And because they miss certain elements, this brings that inconsistent answer that we're going to be seeking. Next thing here is system impact. So system impacts, what we mean by that is basically a lot of these rootkits, in the effort to hide, they actually cause system impacts. Now, this is kind of experimental. I'm just going to touch on this very briefly just to show you kind of conceptually what we mean by that. But it's something that you can look out for, and it's something that can actually help some people who are paying close attention to say, hey, there's something going on here because this system's not performing very well. So the first thing we're going to do with a rootkit is we want to find locating the initialization files. All these rootkits need a way to start up during system boot in order to become active and start hiding, just without exception. They have to get themselves in memory and start intercepting system calls before people start poking around. In the case of this particular rootkit, when we run it, we do the install script. It is immediately going to install itself with a tracker-fs module. That's the actual kernel module. It's going to put in a backdoor called tracker-efs, and it's going to modify several initd and rc files to start itself with the insert module command on Linux in order for it to run. Now, there's a couple of different ways for us to look around here. Now, I would say, first of all, that the way this rootkit runs is when it starts, this word tracker-fs, when it sees that, it does not show that to you in the file system. So once this rootkit is active on the system, you're not going to see any of these files by doing a simple file listing. But again, that little symbol here, my little radiation symbol here, means we're going to look for our first data leak here. There's a lot of different ways we could poke around on a system to see if something might have started. First of all, you could look at the standard files on startup, such as the syslog messages files, the kernel module, the kernel log, and things like that. When it starts, that might give you indication that something might have loaded. In this particular rootkit here, one thing it does is we'll use the system control to list out the tracker, to list out any services that might have loaded, and then we could pull the status from each one of these services. So in this example here, I did a list units of all the services that started and exited successfully, and then I found that list, and I just went through one by one, and I did status tracker fs-service, and here I see my first clue of a data leak coming on, which is the exec start path is showing etc initd tracker-fs. Now, what I would want to do at this point, I'm taking notes during this investigation. I would then write down what all these paths were somewhere in order to investigate them later. But we have our first clue that something has happened on the system, and that is that someone has leaked a path. Now, during that process, I'm going to go to the initd directory, and I do ls-al, and I look down here, and remember, we had a file called tracker-fs, but between S and U, there is no tracker-fs being shown. So something right now tells me that's weird, because This systemd log is showing me that something loaded at this path, but there is nothing here at the path. Now, if I go ahead specifically and I use the stat command, I say, well, look, let's use the stat command, which pulls up the file status information on Linux. I say stat on trackerfs. It says, hey, guess what? There is a file here called trackerfs. It is 101 bytes. I see how many blocks it's using. I see when it was created on the system. So why is stat showing it's there, but the ls command is not? And you can use other commands as well to verify it. You can use cat, stat, file, dd, all these things. You can all use these different, again, asking the same question different ways. Does this file exist? And now we see at this point that there is a file that exists here. And when I go down here to the system, I can actually use the cat command. I do cat etc init tracker-fs, and lo and behold, it's showing me data inside this file. So the rootkit on this particular example hides the listing of the file, but it does not hide the contents of the file if you try to cat it out. And this, of course, makes sense because the rootkits frequently need to read their own data in order to run. So they might hide the location of the file, but they need to actually sometimes access it. So they might be hiding payload data, they might be reading configuration information, things like that. So that's why they need to make it accessible. In this case, what we see here is the insert mod command, insmod here, and it's inserting this path here. Now that double slash is actually an error. It's a bug in the code that is actually legit what it put in here. It doesn't matter. The path is going to be followed. User lib64 trackerfs. So we have another data leak at this point that this path here needs to be investigated. And what we're doing here is we're basically saying that this trackerfs is our kernel module because it's being used with this insert module command. So we've achieved a second piece of information. We have the initialization path where the kernel module is, and now we have the actual kernel module name, which we're going to dig into here in a moment. Now, if you want to check at this point to say, does the system have a rootkit? And let's just say you've seen enough. You're like, okay, there's something weird going on. A lot of these rootkits have a very simple weakness is once you find out the name of the file that it's trying to hide. So in this case, this rootkit tries to hide anything with the name trackerfs in it. If I just make a file here, I'd show you a demo. I made two files. One, I said touch on testing. This is making a 0-byte file. Then I did touch on trackerfs, and I do ls-al. I only see the file testing. The file trackerfs is not being shown. That tells me immediately that there's a rootkit hiding on the system, right? I don't need to go any further. At this point, it's time to call incident response team. We're going to isolate this box. We need to do a full, likely memory dump of the thing and start digging into it to find out root cause analysis of how the person got in. But this is a simple way for you to determine whether or not there might be something on that system. Now, we have pulled out the path where the thing is starting. We have also found the kernel module where it is. So what can we do about decloaking other hidden data that this kernel module might have operating on it? Now, this rootkit was likely, again, based on Reptile, and Reptile has a particular feature where it can actually hide data inside of files. Now, this rootkit, as far as I could see, was not doing that, but it could have. It just removed that capability. But in the base rootkit of Reptile, it has a special feature where if you put between two tags of Reptile, it'll hide anything present in it. So in the case of a Reptile system, I went on here, we loaded up a system with Reptile, and under the etc modules, this is how Reptile is loading itself when the system loads, is it's putting itself in the etc modules files. When I cat out that file, it actually has hidden data. There's malicious data hidden here, but it's not showing you because the kernel module is active in memory and it's saying don't show anything that's here. So this file has data hidden from a rootkit. So one thing we can do if we want to see whether or not a rootkit is hiding files is, again, we're going to look for those inconsistent answers. And Reptile is particularly good at doing this. It can even do it inside an editor. So let's say you want to get tricky and you're like, hey, I'm not going to use a cat command. I'm smarter than that. I'm going to pull up the VI command. It doesn't matter. You pull up the VI command, I'm looking at the same file here, and you can see that the file is hidden that data even inside of an editor. So it's pretty good at what it's doing in this case in terms of hiding itself. But it easily succumbs to extremely simple tactics if, again, you're asking the same question multiple different ways. So what we're going to do here is, first of all, we call a byte count mismatch check. So I'm just going to do an ls-al on the file that I think is having data hidden in it. And it shows me 283 bytes are there. And then I cat the file through the word count command. I say, do a character count, this -c. How many characters do you see? WC says there's 222 characters present. So why does LSAL show 283 bytes here, but this is showing 222 bytes? So at this point, we're missing about 60 bytes, and I can start asking some serious questions about, yeah, these should never be inconsistent. And this is the thing with a lot of these rootkits that people don't understand is, again, it's very hard to make things very consistent across the board. It's one thing to get the kernel to lie about a directory entry, but it's another thing entirely to get the file system to agree with that lie, right? It's very, very complicated, and it's very likely to break the system. And a lot of these rootkits do just enough to do the hiding to work without breaking things. In this case here, this is how we can decloak it. And there's another trick we can do too if we think that there's hiding going on. And this is something I call a single byte read. So a while back, over 20 years ago, in the early phases of network intrusion detection systems, they were often limited by CPU power in terms of what they could do in terms of packet reassembly. So someone wrote a paper about an attack that basically used small fragments from TCP/IP, and the idea here was that the intrusion detection system didn't have the horsepower to reassemble those packets, so therefore you could slip an attack by if you just broke it up into very small chunks instead of doing one big string. And it did work for a period of time until processor power was able to catch up. But the main point here is we can use that same tactic against malware. So what do I mean by that? Okay, so up top here we have our standard rootkit, and let's say I want to hide the file hidden data. And anytime I see the word hidden, I told my rootkit, scrub that from the output. So the hidden data comes in, it removes the word hidden, and on the outside, we just have the word data. Great, but that only works because the rootkit is looking for entire strings of text. What happens though if I broke the file read up into small little chunks, just like a network fragment, and I passed it through? So here, when I read the word hidden in, but I read it in a character at a time, the rootkit is looking for the word hidden all at once. All it sees though is HIDDEN. And then on the outside, what happens is because it didn't see the word hidden as one string, we get the full hidden data coming out there. So basically, we're using a fragmented read operation in order to bypass the string scrubbing and string searching capability of these rootkits. Now, the reason this works is because, again, it's just too expensive. If you think about a rootkit needing to reassemble a buffer of characters and search every one of them for their matching text, they're just not going to do it. It would slow the system down terribly. And as a result, we can get a full read of what's going on. So how does this work in practice? You're thinking, this sounds extremely complicated. How am I going to read a file a byte at a time? Well, it turns out it's actually incredibly simple to do on Linux. In the case of this, we're going to use a simple grep command. We use a grep with a dot here, and that basically means match one character at a time, and we're going to give our path to the file. So here I do grep, one character at a time, etc modules, and I turn the color off here just to make it clear. When I list it out here, I say malicious content below, and lo and behold, our secret content shows up. There's the reptile text. This is hidden malicious file content. There's the close of the reptile. So basically what we've done here is we bypassed the data scrubbing capability of this rootkit. Same thing here. You can use a DD command. I could say DD count. We're going to open up 10,000 bytes. We're going to read one byte at a time. Here's the input file, and then write it out. Same deal here. The file comes out one character at a time. And at that point, we can read the malicious file data. Again, for this Chinese rootkit, they didn't do that, but other rootkits do. These are helpful techniques if you want to actually investigate a system to see if it's hiding data from you. Now, a lot of things all these kernel modules have in common is they will almost always taint the kernel. Now, a tainted kernel on Linux is basically saying someone has loaded what they call an out-of-tree or proprietary or an unsigned kernel module into the kernel space. And as a result, if this kernel becomes unstable and crashes and you pass it into the Linux kernel team to go take a look at it, they're going to say, hey, look, it's tainted. It's not in spec of what we shipped. You should go talk to the people who wrote this driver and see whether or not they're responsible for it. Okay, so essentially, the kernel taint is telling you that something has loaded on here that might make the kernel unstable versus what the Linux kernel team wanted it to have. Now, it can be completely legitimate. There are a lot of legitimate kernel drivers, proprietary drivers from NVIDIA, for instance, video drivers, networking drivers, things like that. So there are legitimate reasons for it. But a lot of these kernel modules that you're going to see from a rootkit level are basically going to taint the kernel almost every time. And we're going to use this in order to see whether or not there's any funny business going on. So one of the first things here we're going to look at is we're going to do a grep on here for just very simply an open parentheses. Now, the way Linux works is if you look in the proc modules file here, anything that is a module that's tainted the kernel is going to have these parentheses with a little letter in it. Now, there are a lot of different letters, but the three most common ones you're going to find are P, O, and E. P is proprietary. And this is an example of a Ubiquity router. And this is showing basically, hey, look, there's a proprietary module loaded here. It's doing something with the IP networking we expect. Or O, which is out of tree, which basically, again, means a module that was not part of the Linux kernel build. So in this case here, we say, okay, well, I see something here having to do with IPsec. It's out of tree, no problem. But the last one here is E. This is unsigned module. I don't have any unsigned modules in this demonstration to show you here, but this is where most of these rootkits are going to operate. An unsigned module is very dangerous. And if you see one operating on a box, it needs to have very close inspection of it. Now, in the case of this rootkit, it is hiding the fact that it has a tainted module present because, again, people, they know, whoever wrote this rootkit, that people are going to look for a tainted module and they're going to say, what is this going on? Why is there an unsigned module of this type E on this system? Now, what we can do then, we're going to start cross-checking to see whether or not our tainted status matches what's actually loaded on the box. So the first thing we're going to do is we're going to cat out proc sys kernel tainted. This value should typically be 0 if there is no kernel taint happening. If there are no tainted modules loaded, this is going to be 0. But the fact here showing 8192, this is a bit mask flag. So at this point, we're saying the kernel is saying definitely something has tainted the kernel. And then what we do here for this system that's infected with this malware is we grep again for that parentheses. And if you notice, remember on the previous slide, when I did that grep, I found all these modules here that were tainted in these parentheses. But on this one, I don't see anything. So here's the thing. This proc sys kernel tainted flag value is showing me that there's something tainted, but this grep command is not showing me any tainted modules that are loaded. So again, inconsistent answer. Why is the kernel saying it's tainted, but there's no module showing up in the proc sys, in the proc modules file showing that it's tainted? This is a big clue that there's something wrong. Now, it is possible a module could have loaded itself, tainted the kernel, and then unloaded itself again. And that tainted state will remain until the system reboots. It's possible that happens. In my experience, it's not very common. Most of the time, if a module loads, it's going to stay loaded. It's going to remain in that tainted state. And it's going to show up in proc modules when you list it out that, hey, I'm the module that's tainted, and this is why it's tainted. But this one doesn't do it. So how do we find out more information about this kernel taint? There's actually a script you can get at kernel.org. We have this in the links at the end of the presentation called kernel check taint. It will tell you why a kernel is tainted. So here it's going to say the kernel is tainted for the following reasons. Unsigned module was loaded, okay? The raw taint value of the int string is E. Remember that I told you about that proc modules E, that unsigned modules is the most dangerous one? This is basically saying the kernel is tainted. It's tainted with an unsigned module. So now we know, again, where is this module, right? We know the kernel's tainted with an unsigned module, but we don't know where it is. So let's go find out who tainted this kernel and if we can dig out any more information about what it is that might have done it. So where are we going to look for kernel taint indications? You just start the log files. The log files are a really great place. There's a couple places we can look for. Some systems have var log kern.log. This will show you the kernel boot messages every time that system reboots. It's going to fill in there what the kernels did when it started up. This is a great place to find a module that loaded that tainted itself. In this case, what we find here is our victim module here. Module verification failed. There's a key missing. Tainting kernel. We did a search for the word taint, and we had this module here, VMWFXS. This is our culprit that tainted it. But again, this is something that we didn't see in the modules listing. So this is our first clue that there's a problem. Again, a data leak has happened here. The second thing we could do is we could check the dmessage file as well. We could do dmessage and we grep the taint. Dmessage is great, but the problem with dmessage is it's a It's basically a ring buffer, which means that it's a certain size. And once it gets too big, it just rolls over the oldest entries and the new ones come in again. So it's possible that the taint message might just scroll out of the message log and you won't see it anymore. It just depends how long the system was running. But this is a quick thing that you could do to check. Another thing I should warn you about are some Linux rootkits will actually hide the taint message, especially in dmessage, but they don't always get it in the kernel log. So again, it's good to check both places. Again, asking the same question in multiple different ways. Another thing we could do is we can ask a journal control file, say, show me all the kernel log types that are tainted or have a signature that's invalid. And again, we see right here, it says instantly VMW FXS has a module verification that failed. The signature or key is invalid. So again, we see the same thing here. VMW FXX has been located in our kernel log. It's in our dmessage, and we also find it in the journal control. So it's what I call the person of interest. We want to find out why this module is not showing up and where the thing has gone to. So how are we going to do that? A couple things we're going to do is I like looking through this proc vmalloc information because this is going to show real-time memory use on Linux for a lot of processes, or in this case, kernel modules that might be using real information at runtime. So we know that it's active in memory right now. So what I like to do, and this doesn't always work, but for a lot of kernel modules, it does. And we're going to search for this bracket. And what that's going to do, oops, pardon me a second here. That bracket's going to basically list out kernel modules that are running and they're present in vmalloc info. It doesn't show all the kernel modules that are loaded, but in this case, it works pretty well for this type and style of rootkit. And we see a couple things here. We see one called DRM KMS helper, and we see another one here, our friend here, VMW FXS. This is our person of interest. But the other thing about VMW FXS is it shows khook init. Khook, I know from experience, is a well-known kernel hook library used in many rootkits. And frequently the functions are not renamed. The fact that they kept this here as khook tells me immediately that this is 99.9% suspicious. All right, this one here. This one is unknown as of now, but we'll find that out in a moment. But this one here, VMW FXS, is active. And what's interesting about this is that, again, proc modules didn't show this module listing, but I know it's active because otherwise it wouldn't be in vmalloc info. So again, where'd you go? So let's go to our next phase here. We want to eliminate whether or not these modules are legit. So the first one here, we found DRM KMS helper under proc modules. I grep for it, and yep, it's showing itself. It's showing me here multiple entries. What this is basically saying is that this module is admitting to the fact that it's present. Okay, and not only is it present, but it also doesn't have those parentheses in it, which means basically that it's actually a legitimate module as part of the kernel distribution. So, but when I come down here and I grep for VMW FXS, again, I get a ghost. So it's not there, but it's in the vmalloc info file, which tells me that it is active. And because those brackets are around it, I know it's operating as a kernel module. So at this point, I am very, very sure that this kernel module is hiding from me, right? Hopefully that makes sense. If it does, please download the slides after this presentation and review them, and you'll see what I mean. Okay, so the next thing here, one thing we could do is we released a free script called kernel module decloak. This basically compares various files on the operating system and will tell you for free whether or not there's a kernel module hiding. For this particular style of rootkit, doesn't work on all of them, but for this particular style of rootkit, it will work. And what we show here is essentially kernel module VMW FXS is active and hiding because we found it in vmalloc info, but it's not in the proc module system. So again, you can go to our links at the bottom of the page and we will show you, again, this script will decloak this module for you. Right, so we found now our kernel module and we want to investigate a little bit more about what's going on. So the first thing here is we found it under the directory called userlib_trackerfs. That's where that ins mod, that insert module command was loading it. We can run a simple file command on it. Now, I would recommend you copy this file to an isolated system before you start poking around it. But for demonstration purposes, we're just going to do it right here on the system. We see it's a system. Interestingly enough, the default does not strip it on this particular rootkit, the default build. It could be stripped later, but because it's not stripped, it leaves a lot of symbols in it that actually make our analysis a lot easier. And then I'm going to run a simple strings command on it. And that strings command is going to show me some really interesting stuff. First of all, first of all, I see the kernel symbols here. This is basically what it's likely using in order to avoid being seen. I see that K-hook reference here, tracker EFS. These filter commands, these would be what it's hooking to help basically hide from directory listings. So again, very, very suspicious. Again, proc root readdir, again, very suspicious. TCP4 sequence show, this tells me that this kernel module has an interest in hiding or obfuscating network traffic because again, it's hooking into the network operations of the kernel. So I know this is likely hiding that type of information. The other thing down here is we see is all these shell references. So it tells me that this probably has some type of backdoor capability in order to run commands, which it does. The next thing we see are various protocols. On this particular rootkit, it uses this proc ACPI PCI card in order to communicate with the user land space. That's unique to this particular rootkit. But again, the fact that it's listed in here means I might want to go look on a system. If I see that present on the proc file system, this kernel module is actually active on the box. And finally, down here, we see some bash history dev null. This is all anti-forensics. Is basically is telling the shell don't record any commands, send them the dev null for the history. This is almost always malicious. You see this type of activity. Finally, a few final things down here too. We see our VMW FXS reference, tracker EFS. These long strings here, these are basically the passwords it's using to authenticate against the backdoor. But there's a lot of information here in this kernel module showing me, again, it's absolutely not a friendly piece of software. I don't want it on the box. It's on the box. So again, we know that we have something really bad going on here. Now, this kernel module does have a backdoor on it, which is, I found actually the most interesting part of how this backdoor, how this rootkit worked was the backdoor. The backdoor itself activates on any port by having a magic packet on it, meaning that if I send a packet to port 443 with a magic packet, it's going to activate on that port. If I send the packet to port number 9322, it's going to activate on that port. So it's any port that's active on the box, it's going to be able to talk to it and have this backdoor work. It enables lateral movement. It has full shell access as well. It can actually chain together multiple backdoors to allow that person to move laterally into the network. It has anti-forensics built in, meaning that it hides not only the command history, which I just showed you in that previous module dump, but also the process itself. Once it's running on the system, it'll hide that. It's got a few weaknesses. It's kind of the hiding is a bit incomplete. So if you are digging around, you're going to be able to find it. You can recover the backdoor binary once it's running if you see the process is running in the box. And the last thing here is really important because a lot of people, they think stealth rootkit, they're impossible to find, this and that. If the rootkit's doing nothing, they could be evasive and hard to find if you're not looking for them. But the thing is, you have to press the attack in order to do things on that box. So the attacker, they're going to load the rootkit, and that's got a bit of risk because when you put a rootkit into the kernel space, you could crash the box. But let's assume they load the system up correctly with their rootkit. They're not just going to sit there, right? They have to do things. They want to press that attack. They want to get on that system and look for SSH keys to steal. They want to steal information, credentials. They want to be able to access information that system's processing. I mean, they're going to be doing things on that system. They're also going to be pressing the attack to move laterally into the network. And all these things give you an opportunity to find out whether or not someone is on that box, you shouldn't be there, and if you need to do something about it. So in the case of this particular rootkit, the way it works is it sends that magic packet as step one, and it will set a particular TCP sequence and IP ID field. When the backdoor, when the rootkit sees that activating that magic packet, it's going to activate on that port. So again, in the example here, we use TCP port 443. It's going to see that packet. It's going to say, oh, this is someone who wants to talk to me. I'm going to activate my backdoor. And when it activates that backdoor, when the attacker sends any future packets to port 443, it's going to encrypt them and pass them to the backdoor binary. Now, the thing is, if you're watching network traffic, you're going to see, let's say, port 443 is your web server. You're going to see web server traffic. And what this means is that you might not see that the backdoor is actually activated because it's encrypted. It's falling in with all the other traffic on that port. It's going to be very, very evasive and hard for you to see. Now, the backdoor is going to spawn on whatever port the attacker wants it to be on. And when they do, again, they're pressing the attack. They're now active on the box. That's going to be a good opportunity to spot them. That backdoor is redirecting all the TCP traffic to that backdoor. And again, all the traffic is encrypted in order to hide. So how does it look from the attacker perspective? Essentially here, we fired up the client. The client is going to port, in this case, 12345. Again, it could be any port. We're using 12345. It's going to say, right, I see a packet. I'm active now on port 12345. And then if I fire up the help command, it's going to tell me everything it can do. I can start a shell. I can upload and download files. I can use this trans command that's going to allow me to move between machines that also have these backdoors loaded. So I could set up a chain to move between these machines. I can even do things such as fire up a SOCKS5 proxy if I want to. But the thing is, it's basically full featured access to that system, and it's running as root. What are some of the backdoors of the shell? Typical things here, fire up, you could start a single command, you could do a full bash file path to run any command you want on the system. You can also do something really interesting here called a -t, this time delay. This time delay is basically, you could set a packet delay of how long it's going to take for a packet to actually work. Like, so when you type a key, it's going to wait 500 milliseconds before it sends that character. I think this is to help evade state-based network intrusion detection rules, or maybe EDR rules, because basically it's waiting for the TCP stream to time out inside the detection system, so then it can go ahead and send the next packet. But it has a few features in here, again, to evade detection, again with anti-forensics, and again, the process is hiding on the box. Other things with that trans command, this is going to allow it to, again, hop between different systems that are all running that backdoor. It's going to send the magic packet. It's going to connect multiple machines and allow that attacker to move between machines while remaining at that rootkit level and hiding the backdoor process on each system, again, to evade detection. So how do we find this? There's a couple different things here. First of all, we have a free tool called Sandfly Process Decloak. This does something called PID busting. PID busting is essentially, we're going to look at all the PIDs on that system that are showing that they're running, all these process IDs, and then we're going to do a manual check to see whether or not they're actually showing up in the proc directory. For this particular rootkit, it works well. This doesn't work on every rootkit, but for this rootkit, it works great. And what we immediately see here when we run it was two hidden PIDs, one called tracker EFS and one called bash, because I fired up again the shell. Again, it gets back down to pressing the attack. They have to press the attack. In this case, they press the attack. That makes these hidden processes vulnerable to exposure. So even if I'm not seeing the kernel module, when they press the attack, if you're decloaking processes, you're going to see these guys on the system. Down here, I demonstrate the fact that if I look at the proc file system, I look for a PID 1075, 1076. I do not see anything. Again, they are hiding. If you use the PS command, you're not going to see them. Use a top command, you are not going to see them. They are going to be hidden from normal system tools. You need to have special tactics in order to decloak them. So please check out that process decloak script that will work on this particular rootkit. Another thing this rootkit does is it hides, again, network activity. If you remember, we looked at the kernel module. It showed that TCP4 sequence show command it was hooking. This is part of what it does to hide network activity. If I use the LSOF command, a lot of people use for incident response LSOF. Great command, right? But in this case, it's not showing the backdoor. It's not showing the backdoor. It's hiding here. I see these listening ports. It's not showing me this traffic down here. But then down here, I run the SS command, and again, I see my listening ports, but there's one here that normally I said, hey, show me all the process owners. So I see systemd here, SSH owns port 22, yep. But here, port 5034, it's listening, and there's like no one there, or what's going on? Again, inconsistent answers. In this case, the rootkit is inconsistently answering the question of what process owns this network port. It has incomplete hiding going on, and as a result, we can see where it is. But more importantly, too, is LSOF is showing a different answer from what SS is showing. LSOF is showing, ports 53 and 22. This one here, SS, is showing 53 and 22 and 5034. So again, they're different answers. These should always be the same. They're different answers. Again, same deal. Inconsistent answers almost always burn these stealth rootkits just across the board in my experience. Right, so let's look then. We found a hidden process. We know it's probably operating on a PID 1075. We decloaked it, that there's someone actually on this box right now. If we do lsal on that proc directory, it is again going to reveal that there is in fact something there, right? We see directly there's something there. We see this exe. I got my full path now to this tracker EFS file, which again, I'm going to be able to use. We're going to look at two files here, the environment and the exe. First of all, for the environment, we're just simply going to do strings on the environment that's in that directory. It's going to show me again these anti-forensics. This bash history is being set to def null. Highly suspicious. If you see people setting this stuff on any process, I would really want to have a talk with whoever it was who started that or look into that system. It's very, very suspicious. Again, though, they're pressing the attack. They want to hide themselves, and by pressing the attack, they've exposed themselves to further detection. Another thing they did here is this exe file. They've running this from this directory. We can recover this file now actually running on the box. Now, this directory is hidden. If you CD'd into this directory here, user include tracker FS, and you did an ls, you probably wouldn't see this file there. But you wouldn't see the directory either unless you know the full path to go to it. But we can actually recover it without doing any of that stuff. The first thing I'm going to do is I'm going to copy the file cp, the exe, to a temporary directory, recover.bin. So here, our process, PID exe to temp recovered bin. At that point, I can run any standard file utility command on Linux on this file. This is going to be the process binary that's running on the host. I can run the file command on it. I can run SHA-512 on it. So I recommend at this point, again, we're going to make a backup copy of this, run it through our standard tools. Be careful about uploading it to public databases at this point to check, because that might tip off the attacker if they're monitoring them. But these are decisions your internal incident response team is going to have to make what you want to do. But the important thing here to understand is that we've recovered the actual process binary. We know that this is our backdoor. Again, though, if I look at this with the strings command, just like in that kernel module, same deal here. I find suspicious things here. Use a local bin. I see some bash shells. It has certificates in it. It has some private keys in it. We can inspect and we can look at a lot of things that are in this particular backdoor binary that reveals more information about the motives and tactics of this attacker. So finally here, kind of wrapping it up, what have we done? Okay, so we found how the module loaded. We found the path to the module. We actually looked at the module to see, yes, it likely looks suspicious. We've discovered tainted kernels that show us that there's a module loaded here that's suspicious. We found out what it was that tainted the kernel, even though the module's trying to hide. We found the backdoor binary process when it was running that was trying to hide itself. It's hiding network connections. We've also looked at that binary and found it's got a lot of suspicious things going on. So the last thing I want to leave you with is kind of an experimental thing. In order to hide, a lot of these kernel modules basically need to do a lot of activity that's going to really impact the system. Now, by impact, I mean some of these kernel modules will simply crash the box. We've seen that multiple times. And the reason is, the Linux kernel is so highly optimized for performance that to think that you're going to write your own kernel module that's going to intercept every system call and you're going to be as fast as what the Linux kernel developers can do is really, really it's just total folly. You're just not going to. So these kernel modules are trying to intercept every process listing command. They're trying to intercept file operations to intercept read-write operations in order to scrub data or to hide themselves in the file directory. They're also intercepting every network call. I mean, think how expensive that is on a system to intercept every network call to see whether or not it's your magic packet and then pass it off to your backdoor. These are really expensive things, and not just really expensive, but they could really cause a system to slow down and crash the box. So to show you what I mean by that, again, this is an experimental thing. I'm not saying this is how you use it to find a rootkit, but for people who are attentive, it might be something helpful to you. I have done here is I've run two different systems. One has the attacker system is clean. This one here, the victim is not clean. I just ran a script that ran a simple find command 100 times in a row. I just searched the word Sandfly across the entire file system just for demonstration purposes. And at the end of that, I could see the clean system took 56 seconds in order to execute this script. But the dirty system with the rootkit took 1 minute and 36 seconds. So it's a massive impact because, again, every time you open a file, the rootkit wants to say, I need to look at that. and see whether or not it's something I need to hide from you. And this is really, really expensive. And so you think about doing this on a really busy box, and these systems were not busy. These are just, cheap systems that we spun up in the cloud for demonstration. But on a really busy system, these rootkits are going to have an impact. And if you're paying attention, you might actually be able to see it. How does it look though graphically? Again, on these two systems here, the top system is clean. I had, I don't know, around a 30% spike in the CPU when I ran this command. The dirty system down here, I had about a 40% spike. So again, quite a significant impact. And again, if these systems are actually under significant load, like they're doing some type of web services activity or database or something, the amount of CPU usage is going to be through the roof. So this hiding that people think is really elite and cool, and yeah, it's fun, but I consider it, more of a, I don't know, like a technical gee whiz thing more than a really good practical application. If you're running these rootkits, you're going to have impacts. And again, if you're an admin paying attention, you might actually be able to find it. So kind of, let me wrap this up on the conclusion side here about these rootkits here. First of all, look, they do work, but I consider them really fragile and frankly completely overblown. People worry about them a lot, but they're so complicated, they can cause a lot of trouble on that system. The second thing here is stealth is great, but it's just like a stealth bomber. Like eventually you got to open the bomb bay doors in order to drop your package, and that's going to open you up to detection. And it's the same thing here. When they press the attack, when they open those bomb bay doors, that's when they're going to really open themselves up to further detection that they might not be able to hide from. And finally, the last thing here is I find just a lot of times people are not finding these rootkits because they're just not looking. They don't have the mechanisms to look, or the security software that they're using in these systems might not really be designed for this type of activity. So it really kind of cripples their ability to find anything. So some of these rootkits can exist for a very long time on a box, especially your older systems that aren't being closely watched. It's really, really risky. So with that here, I'm going to show you a few links. And also, I never do this during a presentation, or I don't do product pitches, but if you stay around for the end of the slides here, I'm going to show you kind of how we do this in Sandfly. And the reason I suggested is, again, what I just showed you in this presentation is really, again, for those tip of the spear people who are going onto a box to do an initial incident response of whether or not this system's impacted. It does not scale, right? So I want to show you an ability to scale. So you can go to our website, you can pull this full presentation down. But what I want to do and what I suggest is we're going to use Sandfly to cheat. So since I have you here on my presentation, I'm giving you privately, you're just going to have to deal with the sales pitch for a bit because it's probably going to be of interest to you anyway. Sandfly is an agentless intrusion detection incident response platform for Linux. We are Linux specialists. Linux is all we do. And as a result, we have a lot of specialized capabilities to find Linux stealth rootkits, plus an enormous number of other attack tactics that are out there. In the case of this particular rootkit, when we run it on a box, even though people said, hey, it's undiscovered, no one's ever seen it before, we immediately got like piles of alerts. Like you can see here, this isn't even all the alerts. We've had like 2 pages of these things. So of these alerts, I'm not going to show you all of them that we found, but I'm going to touch back with some of the ones that were relevant for this presentation. First of all, we decloaked the hidden files. Remember earlier I showed you all these files that were hidden and you had to go through the logs and look for it? We actually found them for you automatically. We showed you all these files here are hidden, these tracker FS files. You know immediately the full path. We tell you exactly what's going on with them in terms of it. So here under initcd contains an entry tracker FS that does not appear when we're looking at the file system. So we tell you the full file system, the full path and everything going on. The second thing we did here is when the backdoor fired up. Remember I had to show you we used a process decloak tool. That works great, but again, we can do it for you at scale, which means we're going to check thousands of systems at a time for a hidden process. And in this system, we found that there's a process PID called 1636 is trying to hide. You see the command shell here, a bin shell. We know immediately that this is probably bad news. But again, we've done all this information for you. The next thing we did is that kernel module I said was hiding. We actually found it for you. Here, the proc vmalloc info is referencing a kernel module called vmwfxs, but it's not listed in the proc modules directory. Again, we're just going to find this stuff for you and do it for you at scale. Again, the manual commands work. They're great, but they're tedious if you have to do in a lot of different systems. And Sandfly, we don't miss this information. Last thing here, again, I'm not going to go through everyone, but this will be the last one. The kernel taint inconsistency, again, we identified it here saying Kernel says it's tainted with an unsigned module. You know, where is this thing? We can't find it. So again, we found all this stuff for you. And this is just a small sample of some of the capabilities in our product. Again, this isn't something I would normally do during the presentation because I don't do product pitches. But for those of you who stuck around and are really interested in it, Sandfly could save you heaps of time. And not just heaps of time, but we're looking for this stuff constantly on the network so we can give you an extremely early alert. And we're agentless, meaning that we could be deployed on systems over 10 years old, all the way to modern devices, including embedded systems running Intel, AMD, ARM, MIPS, IBM Power, IBM S390 CPUs. So you can watch everything from servers in the cloud to on-prem to embedded devices. And we do it without needing to load endpoint agents, which I gotta tell you is a tremendous time-saving and risk reduction capability if you need to watch a large number of Linux systems. So come to our website, give it a try, reach out if you want to hear more. Thank you for listening to a presentation on Linux kernel rootkit decloaking. Again, don't let them intimidate you. Yes, they are evasive, and yes, they do work to a certain degree, but with the right tactics, the right skill set, and the right mindset, you can go ahead and find them pretty easily. So thanks again for watching. I'm Craig Rowland from Sandfly Security. Please check out our other videos. I appreciate your time today. Thank you and goodbye.